This is something the main basis of computer science, where our objective is to solve the problem. And now this FDP is intended to solve our problems and implement our solution on quantum computing platform. Maybe few of you will use quantum logic, quantum machine learning, and quantum hardware, quantum error recovery, and so on. So my request to all of you to please look at this slide very carefully. And when you look at this tree, this is basically I call it as problem evolution, and everybody will agree with this figure that this is already published in my one of the book on design and analysis of algorithm, where I have tried to focus more on the problem solving and problem evolution. So you can see when it goes to the problem solving, first we require problem. And my objective, my request to all the participants here to see that when the problem is given to you to solve, first look into it and see that in which category it goes, whether it goes into sequential category of the problem, where it goes into event based category of the problem, or when it goes to concurrent category of the problem, and then when his example is distributed. So my question to participant again, when it comes to a problem to be solved on quantum computing platform, can you tell me your problem will fit into which one of the category? Anyone? Please answer fast. We have limited time, so we will move ahead immediately. So anybody? There is something in the chat box. Yeah, anybody? Please answer. My question is very simple. When I am addressing your problem on quantum platform, it will go into which category? It will go into sequential, event-based, concurrent, or distributed? Come on, first. Yes? Anybody? Yes, or it none of none of this. So it will go beyond it. And event based, not really, it will not be event based. Anybody? Please answer fast. So it will go beyond concurrent programming, right? And that is what I would like to address first. And then let us go into this branch of the tree, that problem solving requires algorithm, and then you have to decide whether you would like to implement your solution with sequential algorithm, whether you would like to implement your algorithm with parallel algorithms, or the quantum algorithms. Is it clear? Try to understand. Then this also, when you try to look into the algorithmic aspect of any solution, then it requires logic. And the again you have to decide whether which logic is the best choice for your implementation, right? So there are propositional logic, fuzzy logic, predicate logic, and temporal logic. So again, my question to all the participants, can you tell me in the entire computer science, based on which type of logic out of the four which is listed on this slide? Yes, the entire computer science, which logic is used out of this four? Come on fast. Whether it is propositional logic, fuzzy logic, predicate logic, or temporal logic. Please be responsive. Don't worry, your answer can be wrong, doesn't matter. Let me see response in the chat box. Very good, Dr. Nagender ji. It is propositional logic. So everybody should take a note that entire computer science logic is based on propositional logic. Is it fine? So anyway, so this is what, we look at the problem. I will uh, try to see that, majorly in computer science field, we focus more on the computational problem, where the computations are carried out, computations are evolved in the form of one state to another state according to some rules, and the rules which we call it as logic. Is it fine? I hope you are agree with this, that ultimately our objective, basically there are multiple types of problem, like there is a social problem, there is a management problem, and then it's a computational problem. And in our field, in computer science, we generally deal with computational problem mostly, right? So everybody please try to understand, what do you mean by computational problem? Computational problem consists of set of steps. This set of steps are written according to some rules, but always there is change of state. So what do you mean by change of state? There is a use of memory, where computations are reflected with respect to change of state from one place to another place. Is it clear? So this is what we refer to the computational problem. So now my basic question to you all is, can you tell me all our existing machines which we are using? Maybe I'm using my laptop, you are using your computer, PC, laptop. So which architecture is used in all this kind of machine? Anybody? There is a basic architecture. We call it as, very, very basic architecture, which is being followed by all our
Intel,
machines.
Intel, eh,
Intel is not the architecture. Intel,
x86.
yeah.
x86.
x86 is not the architecture. x86 a family of processor, right?
Architecture.
Van Neumann architecture, sir.
Very good. Who has answered this question? Please tell me your name,
Karlekar.
full name.
Nandakishore Karlekar, sir.
Nanda Kishorji, namaste. Yes, good, very good answer. So every computer
Thank you,
which you are using is following von Neumann architecture, right? So Nanda Kishore sir, what is the basic property of von Neumann architecture?
There is an input and output, but there is a system we should have to give there is a transformation between the input and output.
So in single word, how will you define von Neumann architecture? Yes.
Common memory is shared with the processor.
Common memory is shared with the processor. Who is answering this question? Actually, I'm not able to see your name in the screen. That's why I'm asking your name. Very good answer.
Dr. Prem Kumar from Jain University.
Dr. Prem Kumar, where single memory shared by how many processor?
Single
Processor, right? So in von Neumann architecture, it is like, the sequential execution of instruction, and one instruction is executed at one time because there is only one processor.
single processor.
Only one processor. Very good. So that is what I want you all to understand, what is von Neumann architecture. Now I want to shift my problem solving from von Neumann architecture to parallel computer or parallel computation, or parallel algorithm. Are you getting my point? Nalada sir, I hope I'm audible clearly, right?
Yes, sir. Clearly.
There is no problem at all. Okay,
Yeah,
because just I wanted to ensure that we are all connected. So anyway, so now I'm taking a very simple problem. And what is my problem? My problem is to add n numbers. Okay, but not on not on sequential machine which follows von Neumann architecture, but I want to add n numbers parallelly on which machine? Parallel machines. Is it clear? So this is how parallel algorithm will work. All of you are getting my context, how I am switching from von Neumann, I'm shifting my algorithm, or rather I'm shifting my solution from sequential machine to parallel machine, right? So again, try to understand what is the concept of parallel machine. Anybody?
Harvard architecture.
Yes, which architecture?
Harvard.
Yes. So there is one processor or multiple processors? There are multiple processors. Is it clear?
Yes, sir. Yes.
There are multiple processors. Okay, and there is a single shared memory to which multiple processors are connected, and the model is called as PRAM model, right? What is the long form of PRAM model? I will talk about PRAM model in the later part of my presentation, but it is parallel random access memory model, right? Yes. What PRAM stands for? Parallel random access memory model. Is it fine? So look at this very simple approach of adding n numbers. The numbers which are to be added are at the leaf nodes. Okay, and there are 4 processors assigned. So for 2 numbers there is 1 processor assigned. Can you see here? And after every iteration, the number of processors are getting reduced by factor 1/2. Can you see? Please respond to my question. Are you able to understand what I'm explaining to you? Right? So there are 8 numbers, and I'm assigning 1 processor to add 2 numbers. So we will go to the next stage. As you can see, the answer is there on the slide. 5 plus 3, 8, minus 6 plus 2, minus 4, 7 plus 10, 17, minus 2 plus 8, 6. And then at first iteration, there are 4 number of processors. Then at next iteration, there are 2 processors. And in the later iteration, at the final iteration, there is only 1 processor. Are you getting?
Yes, sir.
Yes, very good. Okay. So now what is my objective? This is simple parallel algorithm, which is basically adding n numbers in parallel. And let us try to understand that when we evaluate parallel algorithm, what are the factors, or rather, in computer science, can you tell me parallel, any algorithm is evaluated on which two metrics? Yes. In computer science, we evaluate algorithm, or we check the performance of any algorithm on which metrics? Come on, everybody knows about it. Yes.
Time and space.
Very good. Time complexity and space complexity. But now it is slightly different when it is shifted on parallel algorithms. Okay. So let's see that. So example for 8 numbers. We started with 4 processors. Each of them had 2 numbers in the first step. Number of items are reduced by factor 1 by 2 after every steps. And that is how and the log n steps are required. That is how the basic computer science funda. When the number of iterations are reduced by factor 1 by 2, then how many steps are required? Log n steps are required. Is it clear? And the processor requirement, what is the processor requirement in earlier algorithm? Can you tell me what is the processor requirement in this algorithm? Yes, come on fast. What is a processor requirement in this algorithm? Come on fast. So it is, basically, yes, anybody can answer. It is basically n by 2. Yes or no? But n by 2 is coming to be 1 by 2 into n, and 1 by 2 into n is nothing but n. Is it fine? So the processor requirement is order of n. Is it clear? So just give me 1 second. Hello, I am audible?
Yes, sir. We can hear
Yes, sir. Yes, sir.
Very good. So again, I come back to my same point that how many steps are required? Log n steps are required. How many processors are required? Yes? N by 2. Yes or no? N by 2.
Yes.
So in computer science, n by 2 means 1 by 2 into n. We neglect constant. So finally, the processor requirement is n. Is it clear? Fine. So the question here are, please look into the question very carefully. So how do we allocate task to the processor? This is the first point. Where the input is stored. How do the processor access the input as well as some intermediate results? And we do not ask this question when we implement the same algorithm on this our existing machine which follows von Neumann architecture. Are you agree with me all? Yes or no? Right? So same questions are also applicable when we shift to from parallel computers to quantum computers. Is it clear? Because the basis of quantum computer is again parallel computer. Is it fine? So you'll understand on the next slide. So be ready to understand some mathematics on the next slide. Okay. So what is my next slide? So how do we analyze parallel algorithms? So please, friends, my colleagues, note down there are 3 parameters to analyze parallel algorithm. And these 3 parameters are time complexity, processor complexity, and work complexity. Is it clear? Please understand it carefully. What is time complexity? How many time the steps are required? What is processor complexity? How many processors are used? And what is work complexity? What is the total work done by all processor? Is it fine? Are you all with me? Because I want you to understand this mathematically first so that you will try to map it that how this quantum computing and quantum hardware is doing better than parallel algorithms. Very clear? So in our case,
What's
it
the
is
what's
time
the N here?
complexity.
What's the N here? Small n?
Very good. N is the input size. So time complexity is how many steps are required. Processor complexity means how many processors are there. And total work complexity is nothing but total work carried out. Is it clear?
Okay.
Fine. Okay. So let us take the same example. In our case, what is how many time steps are required? Log n times, right? Fine. How many processors are required? N. So work complexity will be n into log n. Is it clear? All of you understood? The work complexity will be n into
Log n.
Yes.
n
N
into
log
log
n.
n. All of you getting? Nalawade
Yes,
sir,
sir.
slide this time.
Yes, sir. Yes, sir.
Yes, sir.
Very
Yes,
good.
sir.
Very
Yes, sir.
good.
Visible.
Very good. Now look into this. This is something very, very interesting to see here, that to add n numbers, I'm using n processors. Yes or no? To add n numbers, how many processors you are using?
Order of n.
Order of n. Do you think that it's a good approach?
Absolutely not.
Absolutely not. Very good. That is what, because, I don't want to bombard you with theoretical slides. I want you to understand this paradigm shift from sequential to parallel and parallel to quantum mathematically. Then it makes sense to start your research into this field. Is it clear? Okay. Then my question is, what is the approach to that? And that approach is nothing but optimal parallel algorithm. Is it clear? What is
Okay.
that approach? That approach is optimal parallel algorithm. But before that, I want you to understand next 2 to 3 slides, which are more mathematical in nature, but don't worry, I will explain it more clearly so that you will enjoy all. Is it fine? So I'm going to the next slide. And what is my next slide? My next slide is how to judge the efficiency. So please look into it. We say that A1 is more efficient than A2. What is A? A is my algorithm. So we say that A1 is more efficient than A2 if W1 of n can be represented as some function of W2 of n, regardless of their time complexity. What is W?
Work complexity.
Very good. What is W? Work complexity. Example I am giving here. For example, W1 of n is equal to order of n and W2 of n is equal to order of n log n. Are you agree with me? So W1 of n is represented as W1 of W2 of n. Is it clear? Making sense?
Mhm.
Are you getting?
Okay.
So W1 of n is equal to order of W2 of n. So W1 of n is, when it is represented as n, because n log n is there. Is it clear?
Wait. How did you get see W1 of n is actually work complexity? Then how are you equating it to order?
Very good. See, please read the condition. We say that A1 is more efficient than A2.
Uh-huh.
Okay. If W1 of n means if some complexity is represented as function of W2 of n.
Okay, fine. Okay, so functional. Okay, fine.
Function. Very good. Is it clear? Fine. So that's why I already made it clear that please be with me to understand this mathematically so that next discussion would be more clear. Okay. Now, consider two parallel algorithms A1 and A2 for the same problem. There are two algorithms for the same problem. A1 takes W1 work in T1 of time and A2 takes W2 of n works in some T2 of time. But now W1 of n and W2 of n are asymptotically same. What do you mean by asymptotically same? Please.
Almost reaching but never reached it at the end.
Yeah. So relatively they are same, right? Is it clear? Making sense?
Yeah.
Okay. So W1 and W2 of n are asymptotically same. Then A1 is more efficient than A2. Same condition. T1 of n is represented as big O of T2 of n, the earlier example. Making sense?
Okay.
Is it fine? So please try to understand. I'm giving you example here. The W1 of n and W2 of n is the O of n. But T1 of n is, for example, log n and T2 of n is log square of n. Making sense?
Okay.
All of you, please try to understand these fundamentals of algorithmics. And that's the reason, what will be the, when we say that it's difficult to understand, what is the definition of efficiency, but definitely try to understand. In this case, it is very difficult to say which algorithm is better, though A1 is more efficient in terms of work, but A2 runs much faster. Are you getting? A2 runs much faster. So here it is not only, when you talk about parallel algorithm, please try to understand it is not only which runs faster, but it is also important that how many processors you are using so that you can come up with optimized parallel algorithm. Is it clear? So anybody knows that what is the concept of optimized parallel algorithm? Already we are optimizing it as compared to sequential algorithm. Are you agree?
Okay.
Because adding n numbers on one Newman architecture takes order of n time. Are you agree?
Mhm.
Okay. But adding n numbers on parallel machine is taking n log n time, but at the cost of n processor. So is this trade-off good? This trade-off is not good. Is it clear? Is this comparison good? Again, I repeat, one processor adding n number takes order of n time on sequential machine. Fine.
Mhm.
On parallel machine, how many processor? N processor. But total time complexity n log n. Are
Yeah.
you getting?
Yeah.
Total complexity is n log n. So now, at the cost of n processor, please don't forget that. Is it fine? That's the reason. Now the next slide is talking about what is optimal parallel algorithm, and then we'll switch to, if this is clear, then we'll switch to the next part of my presentation, that what are the limitations of parallel algorithm, and then we'll go to the quantum computing and quantum hardware. But before that, I want everybody to understand how this works. Okay. So please see that, consider the problem, and let T of n be the worst case upper bound on serial algorithm for some input of length n. Okay, and maybe this is something we call it as worst case sequential algorithm, and then the best case parallel algorithm. See, it will be always nearby. But again, worst case parallel algorithm, we don't want to get into that. We want to come up with the best parallel algorithm. We call it as optimal parallel algorithm. Is it clear? Okay, so what to do here now? The step one is, please try to understand what is the concept. So adding again simple, the same algorithm, but now work optimal. So what is recommendation is that instead of n processor, how many processors I am using? N by log n processors. Are you getting, all of you? Instead of n processor, how many processors I am using now?
N by
N
log.
by log n
No.
processors, and assigning log n numbers to each processor. Assigning log n numbers to each processor, and then each processor add log n numbers sequentially in log n time.
Okay.
Is it fine?
Yeah. Okay.
Getting me?
Yes.
I want every participant to understand. I'm really happy that at least some participants are responding to me what I'm discussing, but this is something how this is evolving, right? Okay. So now, yeah, Dr. Tadi has raised the hand. Please.
Continue, sir. Continue.
Dr. Tadi Chandrasekhar has raised the hand. Do you want to ask some question?
No, sir. Continue.
Continue. Okay. So now, please see that we are not using n processors, but we are using n by log n processors, and I am assigning log n numbers to each. Okay. So in this case, please see that the work complexity is going to be n by log n into log n. N by log n into log n. And then finally, it is coming to be, order of n, but with only n by log n processor. Okay. This is the optimal parallel algorithm for size n. Making sense? So how many? So now tell me again the trade-off. Here we are, this is my better algorithm as compared to sequential. Yes or no? Please answer to my question. Is it a better option as compared to sequential algorithm?
Yes.
Yes, sir.
Obviously, this is a better option as compared to sequential algorithm, but this is again better as compared to our earlier parallel algorithm, right? This is again better as compared to earlier parallel algorithm. Making sense? Okay. So now, what is our objective? Our objective is to see that how you can do better than this. Unfortunately, today the people who are now doing research or who are planning to do research in quantum, they are not understanding this intermediate paradigm shift on the parallel algorithm, and they are directly switching to quantum part. Are you agree, all of you, with me? Right? So
Yes, sir.
please see that how this transformation is happening, particularly in the algorithmic perspective, so that you will understand that now target is to do better than this, right? And the target to do better than this is nothing but what we are going to talk about quantum, because quantum platform, quantum hardware is still evolving. If you are really interested to see how this quantum hardware works, then we have good quantum hub in the Pune in ICER. Okay, so please plan your visit to ICER. You can see the actual quantum hardware there, right? It's a many crores project funded by Government of India, and the ICER is one of the channel partner to implement this entire research and the lab on quantum hardware. Is it fine? But what is important is just for sake of working in quantum doesn't make any sense. Is it fine? So are you all with me so far?
Yes, sir.
Sir, but sir,
Very good.
sir,
Very
in
good.
step 2, actually, we have only n by log n numbers left. So how this number has come, sir, n by
Yeah,
log
so
n?
n by log n numbers can be now. This is an ideal situation where n by log n numbers left. So we now execute our original algorithm and this n by log n numbers. It's just marginal, right? So what we can do? N by log n numbers. So you can count what n by log n numbers is. So it's only and then you can use according to you can use some sequential number of processors sequentially, 1 or 2. Is it fine?
Okay.
Clear?
Yes, sir.
Okay, very good. So now, so why is this parallel computing important? Because we can justify the importance of parallel computing. There are two reasons. So very large application domain. That is why we are shifting to quantum part, and then the physical limitations of VLSI circuit, right? So there is a limitation to integrate more and more transistors on one chip or more ICs in the one chip, and that is how this that limitations of VLSI. So though the computers are getting faster and faster, user demand is still exponentially growing, because definitely the scale is growing, data is growing, number of users are growing, number of devices are growing, and definitely the existing, even the parallel computing platforms are not becoming adequate to address these high performance computing use cases like weather forecasting, simulation of protein folding, computational physics, and so on. As somebody has already answered, quantum physics is one of the very fundamental aspect of quantum computing. Yes, completely agree. But please try to understand that how this computational paradigm shift is enabling quantum as a better choice as compared to parallel computing. Is it clear? Fine. So now when we say that yes, these are some mathematical foundations of quantum computing, but yes, you have to also see that the physical limitations of VLSI circuit, like Pentium 3, Pentium 4. Now it's recent hyper-threading technology. It's already went beyond nano units. Pentium 4 processor uses 160 nanometer technology. Pentium 5 uses 240 more than that nanometer technology, right? So this is something will come up. No doubt, Intel is the leader in processor, advancement. There are many other leaders across the globe, but still, there it has limitation, because the more and more number of ICs you will pack into one chip, then again there is a problem of power dissipation and better cooling mechanism is required. So you can see, I don't know how many of you are aware about it, but when it comes to Pentium 5, it has about 55 million transistors. Are you aware about it? And the number of transistors on chip is getting double every 18 months. There's a fundamental Moore law that is 1.5 times, right? 1.5 times. Is it clear? Okay, so think about it, and then that's the reason. That's the reason that this entire processor manufacturing leaders in the world has this limitation, and the most difficult problem is to control power dissipation, right? 70 watt is considered as a maximum power output of processor, and as we pack more transistors, the power output goes up and better cooling mechanism is required. Are you agree? Yes, right? So Intel cooled its 8 gigahertz demo processor using liquid nitrogen, but again, liquid nitrogen affordability and the cost and speed trade-off to be balanced. And also, it is also, we have to, or rather this manufacturer also have to ensure that this entire unit is also affordable by a common user. Are you getting, all of you? Right? So this is something fine. The advantage of parallel computing is now already we talk about it, that the speed is we are getting in teraflops. But now our objective is that we do better than this. And there is a concept of hyperthreading in Pentium. So recently all our processors are coming with hyperthreading mechanism. But again, it has that same limitation of requiring more and more cooling mechanisms. Is it clear? So let us not see that this parallel computing is still in use, and there is a lot of efforts in at processor level, like instruction level parallelism, concurrency, and all these factors are being incorporated in the design. But now our objective is that how we can do better than what we have discussed as a parallel computing architecture. So this is a simple PRAM model what we have discussed, but let us see, our objective is not basically to discuss this PRAM model, but now our objective is to see that how this 2 raised to m bits. So the quantum computation is parallel computation in which, this is very, very important statement, everybody is requested to understand. A quantum computation is a parallel computation in which all 2 raised to m basis vectors are acted upon at the same time. Is it clear?
Yeah.
All of you getting? So please understand mathematically, this is very, very important. So if one wanted to simulate a quantum computer using classical computer, if one want to simulate a quantum computer with the help of our existing computer, then one would need to multiply together 2 raised to m dimensional unitary matrices to carry out one step. To carry out one step. Please see the comparison. We are again connecting it to sequential. Meanwhile, there was parallel computing and parallel algorithm in the discussion, which is doing better than sequential algorithm. But still, you can see that what is the difference. So a quantum computer can factorize 250-digit number in seconds, while our ordinary computer requires how many years? You can read 8,000 years to factorize 250-digit number, right? Are you getting, all of you? Yes. Now, my question to you. I will be happy if one of the professor can answer my question. Now, can you tell me, to do this 250-digit of factorization of 250-digit number, how much work complexity will be required if you are designing optimal parallel algorithm? Please follow the same logic what we have discussed. Are you getting, all of you, what I'm saying? Right? So think about optimal parallel algorithm. I have given you the sequential algorithm. It is taking 8,000 years. Right? Definitely my parallel algorithm should take less than this, and my quantum computer is doing it in 1 second. Getting? So what this power is added to this quantum computing and quantum hardware, so that it is so, there is a big gap. It's unimaginable, second and 8,000 years. Right? But still, I want you to understand 250-digit. Come on, n by log n, do it.
600.
Are you getting, all of you?
Yeah.
Perfect. Okay. So let's try to understand the next step. So when you talk about quantum hardware, so qubits are the building blocks. Please understand the building blocks of quantum hardware. Because when you will do actual programming using any programming language, do you know, today, if you want to simulate quantum programming, which is a good platform today, so that you get quantum environment maybe on the cloud? Yes.
Qiskit is one. Qiskit, for example.
Which one?
Qiskit. IBM's Qiskit.
IBM is there, and I will recommend Amazon. Okay, please use Amazon quantum solution. It is far better than IBM solution. Is it? But I am not the ambassador of Amazon, but we have been using for some project, and we have got the subscription for these Amazon quantum platforms. So please try to refer it. Is it fine? Okay, so let's try to understand the building block first. So at the core of quantum hardware are qubits, the quantum analogs of classical bits, right? The quantum analogs of classical bits. So unlike classical bit, like I already discussed, that it can be either 0 or 1, qubits can exist in a state of superposition, allowing them to represent both 0 and 1 simultaneously, right? And this property enables quantum computer to process a vast amount of information at once. Is it clear? Now there should be a question that a qubit is holding value 0 and 1 simultaneously. This property we call it as superposition. Then how this is enabling your quantum hardware to process vast amount of information as compared to previous architectures we had discussed, right? So the next important part is quantum gates and circuits. How many of you heard about quantum gates and quantum circuits? Anybody?
Yeah, we have heard about it.
Yeah, but have you actually simulated it on some platform?
Yeah, some of them, yes. Hadamard gate and C0 and Toffoli gates, for example.
Very good, very good. So, have you used Amazon platform or you're using some simulations?
No, the free software is the IBM, so that usually we get to it first.
Yeah, but it is not giving you the actual realization of quantum platform. It is just
It's a simulator. It's a simulator.
yeah, it's a simulator. It's a simulator. Very good. But that's the reason I'm recommending you to go for Amazon, because Amazon gives you actual
Processing time,
quantum
like it gives the
configuration.
hardware time.
Yes. Very good. But I'm really happy that the participants are very responsive, and most of them are already working on the quantum. But my philosophy to understand this quantum is mathematically how you will be able to you know analyze it. Anyway, so quantum gates and circuits. So quantum operations are performed using quantum gates. Okay, which manipulates qubits through these unitary transformations, and these gates are combined to form quantum circuits. Okay, now there is a difference. See that the entire quantum circuits are just connection between quantum gates, and they execute algorithm by altering the states of qubits in controlled manner. Okay, so that's the reason this. So don't you think that these quantum circuits are also enabled with parallel computations? Yes or no? Are you getting my point? Because at one point of time they are able to hold both 0 and 1 state of qubit. Are you getting? Okay, so they are also internally implemented with a shared memory PRAM model. Are you getting my point? Okay, and that shared memory PRAM model is connected through these different gates, and then that is how your quantum circuits are formed. Is it fine? Now those who have configured a quantum environment, do you know which parameters are more important to configure quantum environment? Anybody? Yes, anybody can answer. Like for simulating network in NS2 or NS3, we have to configure with some parameter, right? Yes. I think one of the professor has used simulator, so maybe you can also answer, sir.
So I've used it in terms of just describing a state first. So a state has to be defined, and then from there we go forward. I'm not sure. I'm not a computer scientist. I'm a physicist. So
Your
my
physicist.
parameters are different.
Okay, great. Anyway, so you have to mention the number of gates to integrate this entire circuit. Then you have to also mention the power dissipation of every gate. You have to also mention the problem size of the input, and many more factors. So please explore this. Anyway, so the next is, I don't know how many of you heard about quantum entanglement. Have you heard about quantum entanglement?
Absolutely.
Very
Yes.
good. So, the quantum hardware is quantum entanglement. So, it is basically a phenomenon where the qubits become interconnected such that state of one qubit can depend on state of another, regardless of the distance separating them, wherever the gates are connected. So, this property is crucial for many quantum algorithms. And, that is how it enhances computational power. And that's the reason, for quantum computing, it requires controlled environment for simulating or actually implementing the hardware structure of quantum. Is it clear? So that's the reason. Please see that this quantum entanglement is very connected to the next point which I am discussing, that is environmental control. So quantum hardware requires extremely controlled environment to function correctly. So many quantum processors operates at even the temperature close to absolute zero to minimize this thermal noise and maintain qubit coherence, right? And they must be shielded from external electromagnetic interference to prevent decoherence, and which can corrupt your data actually. And this is very, very costly. But again, I repeat, if you will actually see the quantum use cases, it is actually used for very, very limited critical high performance computing applications, which is again to be implemented in control environment. That's why I have made it clear that those who are interested to see this quantum in place. Am I audible?
Yeah, we had lost you for a moment, but yeah, now you're
Yeah,
audible.
because I got some error message. Anyway, but now it's fine.
Yes.
Okay, fine. So again, I repeat, I'm going back to the previous slide. Qubits, quantum gates and circuit, quantum entanglement, and then this control environment. There are two more very, very important points. There is a lot of I can see there is I think one of the session on error correction and detection in quantum, right? Nalade sir, I think it's that session is there tomorrow, or I think day after tomorrow.
Yes, sir. Tomorrow, this
Yeah.
session we have scheduled.
So I request all the participants to please take it very seriously, because this is one of the very, very interesting area in quantum hardware part. So, this entire quantum systems are actually prone to internal errors due to this decoherence and operational imperfection in the design, in the deployment. And, this is very critical research area where objective is to develop the methods to detect correct error without measuring the qubits directly. Okay, so try to understand, without measuring the qubits directly, which would collapse their quantum state, because these qubits are very, very delicate in nature, because it is taken care by the high performance computing platform where it is in the both the state 0 and 1. So this is very, very rather one of the national mission for government of India to have this error free quantum systems. Okay, and everybody is requested to look into it very carefully, because or rather those who are really interested, then pick up this error correction and detection as one of the research area into this bigger picture as a quantum. And then when you look into the hardware types, so there are multiple types of hardware exist, like superconducting qubits, trap ions, topological qubits. But yes, everything has their own advantages and disadvantages. But yes, choice of hardware depends on, what is the scale, what error rate is affordable, and then, the overall performance of your quantum computers. Anyway, so this is something, the most of the time I don't know how many of you heard about the NP hard and NP complete problems. But now let's see mathematically how this qubit works, and then you will be able to understand that the eigenvalues and eigenvectors, how they are measured with the superposition principle, and the quantum measurement, how this quantum measurement is measured. It is always absolute in nature, right? So because it is absolute in nature, because it can be both in state 0 and state 1. And then, the question is how to implement this unitary operator. So the answer is introduce a complete set of logic gate, and all these logic gates are based on, the singular matrix operation, which generally we perform in the linear algebra. Okay, so again, you have to go back to, but it's fine. Now most of the people are doing up, the not the fundamental research, they are doing applied research. So what is applied research? They are building something on the top of this quantum platforms, and they are rarely concerned with what is happening internally at hardware level, how this quantum OS works. Now there is a quantum machine learning. I can also see that there is one session on quantum machine learning, right? So quantum machine learning is coming up. Then quantum machine learning means building something with this quantum environment and then extending all these ML and existing algorithms on this quantum platform. Anyway, so the next is the basic. We'll touch about the superconducting qubit devices. So any quantum mechanically coherent system could be used to implement these ideas of quantum computation. Can be single photon, nuclear spins, trap ions. Already we talked about it, but it has its own advantages and disadvantages. Anyway, but I would like to up in next 2 minutes. So it is basically designed, these unconstrained binary problems, which generally goes into the category of NP hard. Okay, so there is a company, we call it as D-Wave Systems, and if you go to of this D-Wave, the hardware simulator or programming interface is available on this D-Wave platform. Is it fine? Okay, so those actually who are interested to explore this, uh, you can go to this platform and you can try to explore this. Is it clear? Fine. So there is a question that is there in the chat box, that is it possible to explain how transistor level design in quantum superposition works? So please, you have to first understand how this connecting gates, as we had discussed on the last slide, that how this vector eigen vector multiplication and eigen matrices are multiplied, and if you are able to optimize that, then it will be able to possible for it will be possible to for you to understand this transition level design in quantum superposition. This was a question by Mundu, right? Anyway, so